Hello students, in this video we'll find the Schwarz Christoffel transformation from the upper half space onto an isosceles right triangle. So let's recall, we need a couple things. We need 3 points, k1 plus k2 plus k3 to be equal to 2. Those are the exponents. And we know that ki is equal to 1 minus theta I over pi, right? So let's figure out what these ki values have to be. So let's say k1 and k2 are the 45-degree angles, right? So if those are 45-degree angles, that's pi over 4. So k1 equals k2, and that's going to be what? It's k1 equals k2, and that's going to be 1 minus pi over 4 over pi. So that's going to be a 3/4. Good. And then what would the other one be? Well, if I have 3/4 plus 3/4, that's going to be 6/4. I need another half, right? This is going to force k3 to be equal to 1/2. So I have my points now. Good. I have my exponents, my Schwarz Christoffel transformation. Okay. And so now this will correspond to what angle? So now our angles are going to be what? Our triangle is a 45, 45, 90 triangle, right? So it's an isosceles right triangle. Cool, right? Awesome. That's like more like the high school geometry way of saying it, right? So 45, 45, 90 triangles, isosceles right triangle, right? But for us, we know it's like pi over 4, pi over 4, pi over 4, pi over 2, okay? Good. All right. And so now I'm going to choose this points symmetrically, right? So let's pick x1 to be -1, x2 to be 0, and x3 to be equal to 1. I'm going to map those 3 points onto the vertices of the triangle. Okay? How are we going to do it? So there's one modification. I need to rotate my frame a little bit. So I've already pre-done this problem where I figured out what the rotation factor is. If you haven't pre-done the problem like this, just say like I need a constant in front of this, which is going to rotate, right? So I just did a rotation constant. So my function is going to be the following. My f of z, my Schwarz Christoffel, is going to be e to the 3 pi I over 4, the integral from 0 to z of a zeta plus 1 to the -3/4, -3/4, and then a zeta to the -1/2, that's my right angle, and then a zeta minus 1 to the -3/4 d zeta. Okay? This is my Schwarz Christoffel mapping. Okay, excellent. All right, so what are some of the easier things to do, right? So the easiest thing, of course, is look at W2 first. Let's do the easy one first. W2 is f of 0. F of 0 is what? Integral from 0 to 0, 0. Got W2. Phew, if that wasn't so bad. Let's do W1 now. W1, so we can do W1 or W -1. Let's do W -1, right? What's f of -1? F of -1 is going to be e to the 3 pi I over 4. The integral from 0 to -1. Let's figure out the argument changes over here. So in other words, if we're between 0 and -1, what's happening? This thing is okay still, right? That's a positive real number. So I'm just going to put modulus zeta plus 1 to the -3/4 with no argument change. Over here between this and this is going to change, right? So it's going to be modulus of zeta -1/2. And then what's going to happen to the argument? It's going to be an argument of e to the I pi. So it's going to be an e to the -I pi over 2 times what? This thing also is going to change. I'm going to put a modulus zeta minus 1 to the -3/4. And then the argument over here is going to be an e to the I pi. So it's going to be e to the minus I 3 pi over 4, right? Excellent. D zeta, like so. Okay. Now let's calculate these things. Well, e to the -3 pi over 4. This thing over here is going to cancel with this. That's why I chose it. Okay. And then what's left is this e to the -pi over 2. That's going to be a -I, right? So this is going to be -I. The integral from 0 to -1. And then I'm going to have a what? I'm going to have an I'm going to have a zeta squared minus 1 to the -3/4 power. And then a zeta to the -1/2 d zeta, right? I can replace zeta with replace zeta with negative zeta. That will induce a negative sign. And that will fix my limits, right? So if this is going to be equal to I, the integral from 0 to 1. And now I just have a zeta minus 1 to the -3/4, and then a zeta to the -1/2 d zeta. Okay. Now what I want to do, that maps to the point I, is I map straight up, right? So I go from, this is my point, W1 is mapping on it's on the imaginary axis. It's an imaginary number. Let's figure out exactly what this integral is equal to. So what I'm going to do now is I'm going to let u be zeta squared. So that says that du is 2 d zeta times zeta. And of course, zeta is root u, so this says that du over 2 root u is equal to d zeta, right? And so if we do this, what's going to happen? So let's look at this over here. So now, what's going to happen is that my integral is going to turn into what? It's going to turn into the integral from 0 to 1. The limits don't change. Then I'm going to have a u squared over here. And I have to correct this over here. So this is not quite correct because this is going to be negative. So I need a 1 minus zeta squared over here. 1 minus zeta squared.
Good news.
Okay, that's much better. Okay, now it makes sense. Okay, and then that's going to be a what? That's going to be a 1 minus u. So 1 minus u to what power? To the power negative 3/4. Then we have a zeta, which is what? Which is root u. So that's going to be a u to the 1/4 power, negative 1/4 power. Then a d zeta, which is going to be a du over 2 root u. Okay? Excellent. And so what this is the following. So this, of course, is just going to be equal to 1/2 the integral from 0 to 1 of 1 minus u to the negative 3/4 powers, and then u to the negative 3/4 powers, du. And that is just what? This is exactly just 1/2 the beta function at 1/4, 1/4. Beautiful. So that's the beta function. I'm just going to call this parameter over here, call that parameter just b, okay? So in other words, this gets mapped to the point. The f negative 1 is just going to be mapped to I times b. Excellent, okay? That's just the beta function. You can write this in terms of the gamma function now, okay? And now the final step is to look at, so we have, that's my, I of b is my w what? w1. Good, so IB is W1, where B is this parameter over here. Next step is to look at the final point, which is going to be f of 1. So f of 1 is W3, so W3 is f of 1. And f of 1 is going to be what? It's going to be e to the 3 pi I over 4, the integral from 0 to 1. And then I'm going to have a what? No argument change over here. No argument change over here. Now an argument change over here, right? So that's going to be a what? That's going to be a zeta minus 1 to the negative 3/4. And then e to the minus what? E to the minus 3 pi I over 4 d zeta. Oh, look at this factor over here and this factor over here. That's why I chose them. Those two factors cancel out. And you have the f of 1 is just the integral from 0 to 1 of what? Of 1 minus zeta squared to the negative 3/4. And then zeta to the negative 1/2 d zeta. Oh, we already did that calculation over here, right? This calculation says this is exactly equal just to what? Just exactly equal to the value b. Beautiful. Now what's happening over here? So what's happening over here is here's our upper half space. Here is negative 1, here is 0, and here's 1, okay? Negative 1 maps where? This is our Schwarz Christoffel mapping f. It's going to map it over here, like so. It maps negative 1 where? It maps negative 1. Where's negative 1? It maps negative 1 to IB. So that's negative 1 goes to IB. Then as I go to 0, I go down. F of 0 is equal to 0. So I go down over here to 0. And then as I go over here from 0 to 1, going from 0 to 1, I go from 0 to the value b. And now, as I go to infinity, as we go to infinity, what happens? I go from 1 to negative 1. Going from 1b to negative 1 IB, I go like this. It connects them like that. What kind of a triangle is this? Oh, that's a right angle over there. That's 45, that's 45. I've mapped the upper half space onto this isosceles right triangle. Very cool, because now what I can do is if I'm able to actually analyze, if I'm able to say here's an analytic function, take the complex conjugate and then find a primitive of that, then I can find the streamlines of an incompressible irrotational flow inside an isosceles right triangle. Very cool stuff. And so you can simulate that very easily, right? And so it's very worthwhile to find a simulator where you can actually simulate the streamlines using these Schwarz Christoffel mappings. In further videos, we're really going to try to say, well, it's more natural. You don't want to think of like an incompressible irrotational flow in a triangle. It's more like you want to do like a channel or over a slit or over an obstacle, more classical fluid things. How do you flow over a corner? How do you flow through a slit? How do you flow into a channel? Those are more classical problems. We'll address those, or double slits. We'll address those problems in further videos, but for the time being, we want to focus on some of the classical geometric configurations of Schwarz Christoffel mappings, because they're neat. They're neat to see how you would do these mappings from the upper half space onto a simply connected domain, like a triangle, for example, right? That's a simply connected domain. The question becomes is, we know by the Riemann mapping theorem, which we've yet to prove, we will prove that eventually, by the Riemann mapping theorem, any simply connected domain and by our two simply connected domains are biholomorphic, right? That are not the entire complex plane, right? So, in other words, proper simple connected. We have to specify what we mean over there. But very, very useful construction. Now, of course, the idea is that what you want to do is you want to say, when do I choose? We've seen examples now where we only choose two vertices and let infinity be the final vertex point. And we've seen now examples where all the vertices come from the actual complex, come from the real line itself, right? So it depends on the symmetry of the problem, right? Sometimes the symmetry problem says, let's choose all the vertices on the real line, like for a rectangle or an isosceles right triangle. For an equilateral triangle, we will let one point be infinity, right? And so in other examples, we'll see, like for a square, for example, I'll let one point be infinity, right? And so sometimes choosing infinity to be a vertex is good. Sometimes it makes the problem more complicated. Sometimes we just need to exploit the symmetry and just tinker with this formula a little bit, because all these Schwarz Christoffel mappings have one of two forms. They look like linear functions of these integrals over here with n-1 points or with n points, right? So just a matter of figuring out which one you want to do to make the problem simpler for you. Thank you very much.